So the next talk is from Helen Usher. You're doing a PhD at the Open University at the moment. Is involved a lot with schools in South Wales, promoting comet observing as a way basically to get kids interested in science. So I'll hand over to you now, Helen, and I know you've got some visual aids as well, which are good fun. So let's get this going.
Good morning. I could probably say that Alan Fitzsimmons over there is probably my PhD supervisor grandfather, even though he's probably only about the same age as me. Alan's PhD student was Colin Snodgrass. Colin Snodgrass is my PhD supervisor. So we're going through down in the age and back up again. So I've come at this late. I was a long-term amateur astronomer until 5 years ago, at which point, having got completely hooked on the Rosetta mission, and there was the chance to come and do some work on the amateur data set from the Rosetta mission. It's proving challenging, but I will get there because my family won't let me not get there, given the amount of time and effort we put into it so far. I also work with schools, which is why I have a fluffy comet, and we have a rotating penguin. Now, I think at this point, you say never work with animals, children, well, probably rotating penguins might come into this as well. So, I'm based in South Wales, so I work a lot with Cardiff University. And the work that we're doing is very much collaboration, whether it's with amateurs or whether it's with schools, and we're trying to draw that circle of collaboration as big as possible. And a shout out to Richard, who's here, and Tony Angel, who would love to be here but isn't, because they've been working really closely with us on all of this. So, context. My research questions, these have morphed a bit, and they may morph a bit more before I actually write my thesis, because I think you write the questions after you've written your thesis. So. But you can see where, particularly today, the first two come in. So what can we learn from the Rosetta mission about how we organize campaigns? I've also looked at other campaigns, whether they're Comet campaigns or other observing campaigns for hot young stars or whatever. What can we learn? How can we do it better? Then how can we use those missions to, say, draw a bigger circle? Can we work with educators, amateur professionals, astronomers, to engage, enthuse, inspire, all the standard STEM buzzwords? But can we get kids who are having fun, enjoying themselves, learning things without them thinking they're learning things sometimes, but teaching curriculum skills? And then finally, when I've got all of this data, what does that tell us? So that's the last bit of the PhD, and that's will be coming tail end of this year, hopefully, beginning of next year. So for today, I'm just going to concentrate on the first two quickly. What can amateurs add? There are thousands of you. COB's database says there are 2,500 just about active observers. You've got wide geographical coverage, high quality equipment now is getting better and better. What you can do, where you can do it from is now, if you've been an amateur astronomer 20, 25 years ago, you wouldn't believe how much has changed. You can do things that the professionals can't. Observations at low elongation, low altitude. Our big domes are fab, but you can't see the horizon. And how many of us have gone on tops of mountains just trying to get that less 5, 10 degrees of sky so you can see the spectacular things that tend to be close to the horizon? You can respond quickly. You don't have to fill in the telescope proposals that say, in 9 months' time, I think I might be interested in, and it might do something at 10 o'clock at night, and can I be there, please? When Richard says 29p is exploding, we can go, okay, we get our telescopes on it. And you can run all night, as opposed to I've got a half an hour observing window or whatever. You can observe things that you can then say to professionals, this is really cool, can we have a look at it, please? And then they can perhaps go for director's time on telescopes and get some good images. You can go for Hubble, JWST, or whatever. And the range of things. Nick was talking about looking for binoculars because they've got a huge tail. If you're looking at that with a professional 2-meter telescope, you're not going to see it all. You're going to see the middle bit. You're not going to see the rest of it. So you actually need different scale images if we're going to say what all of this is together. So you can add loads of things to professionals. And I've done some analysis of the data set for 67p about gaps. There are 15 dates, even with the 67p Rosetta mission, which would have been more observations of a comet than anything else ever. There are 15 days where there's no professional data, but you as amateurs have got data. So you can plug gaps. There are times where there's a gap between professional things. We can plug it. Now, Peter's here somewhere. There's a chance, Peter, you might be able to constrain an outburst because there's a 5-hour gap in professional data, and we've got amateur data in there. I haven't done the analysis yet. It was a very faint outburst. The probability is low. But if you'd done something spectacular, you probably would have helped. So we can add real value. This is the COBS database as of a couple of weeks ago. You can see we've got thousands and thousands of observations in there. And now as it gets to more CCD, more visual. There's a challenge though. Can you see the spread on this? We're all allegedly measuring the same thing, except if you're looking in the middle here, we've got what, 5 magnitude difference? There's some challenges there. Now, 46p was an outlier. It was huge. So what you measured made an awful lot of difference as to how bright it was. So sometimes when you're trying to prove a point, you go for extreme. So consistency is a challenge. This one I quite like. It's 6, it's 9, it's 6, it's 9. So how bright is the comet? Like, people would do stars and asteroids. It's easy. You know what you're going to measure. It's this big. You just measure it. Comet. So I think we need some standardization. This is what we've been looking at. Looking at simple to use pipelines that are consistent. And if we can get it right, we can work with old data and rework it as well. So we've been working, is it a year already, since the Pro-Am workshop in Prague. And actually we were at the Asteroids, Comets and Meteors conference in Flagstaff the week before last, which is why I'm looking somewhat haggard, because it's all been a bit manic over the last couple of weeks, because the National Astronomy Meeting has been in Cardiff in the last week as well. So what we want to do is, as a starting point, there's lots of good data out there. We just need to work out where it is. And if we could get it so that you could put one query in that says, tell me everything that 67p did in this particular period, it goes off and it finds the data for you. So we're working, we're hoping to put a VESPA submission in this autumn. That's a Europlanet funded scheme that puts that front end in. There were some things that came out of the Flagstaff conference a couple of weeks ago. There's some people over there that are thinking of doing something similar. Whether it'll get off the ground, I don't know, but there's some conversations to be had. Then we need to improve consistency. So as Nick said earlier, we've got a little Royal Astronomical Society grant to do some testing on RNG or primes and G prime filters to see whether if you match a catalog to the actual filter that you took the data with, rather than having to put in some conversion factors, whether we can get a bit of consistency in there. And using the same catalog, because people use different catalogs. And if we can start to standardize the apertures, and if we can get pipeline processes where it's easy to change the aperture, then you just plug in the numbers and it runs it multiples. And perhaps if we start doing it on a physical scale at comets, instead of 5 arc seconds, if we say 10,000 kilometers at the comet, then we get a bit of consistency as well, as depending on where the comet is. So a couple of pipeline pilots under the way. Nick has been working on some stuff. If you've read The Comet's Tail, you'll see Dennis's interview with Mike Kelly. Well, we were talking to Mike Kelly the week before last, and Kai, who is my colleague who in Cardiff, is working with Mike to see if we can get that consistent process. Because if we've got the same process that the people who are looking at outbursts are using, then hopefully we get comparability. And Daniel Gardner at Edinburgh, who's another one of Colin's PhD students, he's been working on the 67p Pro data. So we're working on his pipeline as well. So there's some things in train there, but we need to make sure that it's easy to use, because it's okay for the computer geeks to be able to do it, but we need to be able to get it so that anybody can use it. and batch processing, because you've got lots of data, then just pushing a button and doing it. At least then if it flags up something's changed, then you can go perhaps in and do a bit more detailed, but as a first stab. And I'm really interested to see what Thomas is going to tell us about later as well, because I think there's lots of good things going on, but how do we pull them together? The thing with this is it needs good FITS header data. So please, if you're submitting images, remember to change your FITS header data. This is my long-term project. Collecting raw data, rather than collecting pictures, collecting raw data. Non-trivial, I think, is what somebody said to me last week when I was talking about. But we think we can do it. We're going to try some small scale stuff where it checks the, it asks you to tell us what system you've got, and then it checks that as a first point. And it'll then rewrite the FITS headers. It'll give you a table that says, these are the observations we think you've made, check they're okay. If they're okay, it uses that table then to rewrite the FITS headers and zips them all, and you can batch upload. So trying to make it straightforward. But I am not an IT guru. If you see my code, you will see that. We're just trying to proof of concept, really. We need somebody to pick it up and run with it, because the problem with a lot of the things that we as amateurs do sometimes is that they're brilliant, but they're dependent on the individual. And when that individual decides that life goes in a different direction or something, how do you keep the continuity on it? So can we talk to NASA, ESA, Hawaii, Edinburgh, Europlan? We'll take money from anywhere. We'll take expertise from anywhere. Anybody wants to come up with expertise? We're there. So that's what I've just been talking about. It's basically a process that validates what we get. And then for campaigns, how do we actually make sure that we can communicate it properly? And this is where what Richard does, I think, shows it doesn't have to be that complicated. You can do with a simple web page and a mailing list. Alerts, two-way feedback on what's coming out of the science as well. But it does take active management. And I think if we do it on bulk, then that's going to be a bit of a challenge. So some questions for you. Would you sign up to an alert system? How much certainty would you want? Would you want somebody saying, it might be, okay, I'll go and have a look. Or would we say, yeah, I'm sure something's happening, go and have a look. And how would we do it? And then some questions, if you want to find me, over lunch or whatever, what tools do you need to be able to get involved? And then this one is, I think, one that I think for BAA is a really important one. We've got brilliant, knowledgeable people. How do we extend that? How do we make the pool of people bigger? How do we make sure that we've got expertise and consistency? So guidance, training, mentoring, bite size. Can we turn the wonderful guide into a series of 15-minute bite-sized videos that somebody's there? How do we make it interactive? How do we link people up with people who want to start? Do we start with observing challenges where you get people to work through a known set? So let's make our pool bigger, and if we can make it more diverse, brilliant as well. I'm actually quite surprised we've got quite a lot of women. When we were in York for the last Comet meeting, there were 3 of us. So yes, we're getting somewhere. And then mentoring and public and school outreach as well, because the BAA objectives are not just about science. There's a small part about science, there's lots about public engagement and outreach, which takes me nicely on to Comet Chasers. This is where I am actually training the people who will be Colin's PhD students when the Comet Interceptor mission starts coming back with its data at the beginning of the next decade, because my 10, 11-year-olds by that point will be BSc and students. So delivery team, Cardiff-based mostly. Ben Woodin is our school teacher, and then we have Richard and Tony as our observers who work with the schools through the hands-on stuff, and it's brilliant. If you've got more BAA members who want to do this, then please come and talk to us, because that in the background stuff, even if it's just working through a data set, filtering out the ones that don't work with Astrometrica. That makes it much better when it comes to schools, because we all love and hate Astrometrica, don't we? It's brilliant when it works, and when it doesn't work, problem solving is a nightmare. So if you can just take all those out, so the school knows that when they want to run through their data, it'll work. Because what we're doing is about science and scientific method, so hands-on sessions and experiments. And this is Chewy, who is our Comet Chasers mascot. So he comes out with us, and the kids love throwing him around, basically. But it's very hands-on what we're doing. And the way that we run this is it's not just about science, it's about all the curriculum skills. It's about teamwork, it's about communication, it's about experimentation, etc. But we use this on a mission as our hook. So we've been on a mission with 67p observing it a couple of years ago. For 46p, we're on a mission with 29p. And recently we've been on a mission with the DART mission. We've really been on a mission with NASA. And I'll get even more excited when I tell you about that in a moment. But the great thing about this is that we're actually linked with the Focus Telescope project. So we get access to 25 research class telescopes across the world from the classroom. If you know people in the classroom who want to get involved in real research, come and talk to me, because we can link you up. And that means that the schools can do it from their classroom, but the data that comes out of it is real research data, so the scientists use it. And we're collaborating with the LOOK project, which is one of the LCO other projects, which is looking at outbursts. So it's taking like data from ZTF. There's an alert that says there's something here, and our schools love it when you can say to them, quick, go and have a look at something. Is this breaking up? And they go, they're going to have a look. Or something is outburst, can we get some data? And they're getting credits in research papers. So schools actually named, you know. And we do very hands-on. So we do everything from making comets out of blobs of blue tack and string, and to, we have to do galaxies because sometimes comets are boring, but galaxies aren't. But we can do Messier and say, we can do galaxies in Comet Chasers because, well, Messier was looking for comets when he found his objects. So hands-on, you know, bits of Moon and Mars, making a comet, you name it, we do it. But it's hands-on. So activities for students, support for teachers. And at the moment, we're doing it in English and Welsh. As a result of Prague, we're also working with Jan in Italy. So he's been translating some of our materials into Italian. And our new curriculum in Wales is far less siloed than it is in England. So it's more about your skill set, all the things you pull together, and what we do just fits really neatly in that. So we're working with new resources for schools, for the poor teachers who've been running things for a long time. And so, you know, it was incremental change each year to now, I can't use that anymore, I need to do something else. So we've been working with them. And it's about raising aspirations as well. We work with a lot of very deprived primary schools primarily. And here we are, our name in lights. This one, yeah, so we're with Michael Kelly. Alan will notice this one because this was 248370 was when Alan put an alert out that said, we think it's a main belt comet. And within 12 hours, our schools were on it and taking data. So in the credits of the proper research papers, and I've got pictures of the kids holding up going, yes. So our latest one, DART mission. We thought DART mission where you crash a spacecraft into an asteroid would be quite good fun for 10-year-olds and 59-year-old, 10-year-olds like me as well. So we went to RAS and said, I'd like to give us a bit of money to do this. And they said, yes. So what we've been doing is getting kids to look at asteroid and comet properties. So handling meteorites that says, you know, this is real stuff. Investigating impacts. So how much of a hole can you make if you, and I'll show you a simulation of that, and you can all play with it later if you want. What makes a killer asteroid? How big is nasty? And then learning about why DART is really important to avoid the killer asteroid. So the kids make their comets on a stick, and we do the dust tail and the iron tail. We have a hairdryer, solar wind. You can see we have gravity, how does it work? Yeah. My favorite one, as you can see, we did this in COVID, is the crispy Comet one. So if you look at our Comet Chasers website, we have a try this at home, and it includes the Comet set, because we do 2 different mixtures of Rice Krispies, because comets are actually, really, there's a lot of air in comets. So if you do a different mixture of a different amount of chocolate compared with Rice Krispies, you get a different consistency. So we get them to try and make 67p in Rice Krispie cakes with 2 different mixtures, and then we get them to chill it. So you can see how comets are more stable when they're colder. And then, because scientific method means you need to test, when they come out, they have to eat them and write their report about which one was easiest to eat. So it's all science, but so. Then we have impacts, killer asteroids, and DART. If you actually look at this website, it will allow you to vary, if I can do it exactly, the input parameters. So how big a meteorite are we looking at? A bit of an asteroid. What angle is it coming in? How fast is it going? Where's it gonna, what's it made of? Where's it gonna land? Now, if you've done anything with 10-year-olds, you know they do biggest, fastest to try and blow the biggest hole possible. What you can do is you can then, once you've done all of that, you can choose where to locate the center of the crater. And you know where they're going to do this, don't you? You know they're all going to say, where's my school? And I love doing them, because when you do that, and you can see how big a crater you got, and then you go to them, so where's your house? Oh, so I've just blown my house up as well. I did have one kid in Leeds a couple of years ago who was scrolling through, because you can do anywhere on Google Earth, and he was in New York. I'm thinking, what are you doing? I'm looking for Trump Towers. Who knows? But what we can get the kids to do is to see how changing the parameters changes the size. And we can say to them, what's the smallest hole you can blow, biggest, deepest, shallowest, etc. And how does the different gravity and atmosphere change as well? So you can do Earth, Moon, and Mars. And with the moon, you can actually get them to see if they can match the crater size to the craters on the moon. So they get a feel for how big an asteroid might, an impact it might have done it. And that's why DART's important. So we also learn about light, and this is where my penguin comes in. Why are we rotating a penguin? Well, if you're trying to say to children about something that is a bit abstract, like light curves, but if you could show them, well, we're onto a winner then, aren't we? So here we have a simple thing where we have a torch, a simple webcam, and something to start with that is just black and white. And if you can see my light curve, it goes the top when it's bright and the dips when it's black. From that, you can start to get them to work out how fast it's rotating. You can see the ratio of the black to the white. And if you put a brighter torch on it, see it gets brighter, etc., etc. So real-time, hands-on, and then we get them to basically put anything they want on there. So Turi with his main comes in. We have various types of decks because 67p comes. We did ones for Didymus mission, where you have the moon, the asteroid and the moon, and you can see how the light curve changes with those as well. And then they put pencil cases and they work out how many decks they can rotate at once without them falling off and things. But it's all about being sure that when they come to setting up the telescope observations, start to the measurement, they know what they're doing and why they're doing it. So real time. We got them to do before and after images of Didymus. Not just to show them the change, but for some of the schools I'm working, well, if you say, would you like to work for NASA? Yes. Do they believe they can work for NASA? No. By lunchtime, you'll be working with NASA. And so we went in before so that when the DART mission actually got some coverage on television, they can say, I'm part of that. Which, when you're a 10-year-old in the valleys thing with really low aspirations, that's actually quite cool, isn't it? And it wasn't just a case of we were doing the same thing as NASA. because the LCO network was part of the NASA official mission, our data set are actually going in there. So when they presented the DART change data at the Planetary Defense Conference, schools named on the bottom because our data was in there. So really involved in it. And the DART mission team have been brilliant with us. They've been sharing our stuff. So this is our rotator. We'll go quickly. These are kids actually setting up the big telescopes in their classroom. I spend a lot of time on my knees on these. But this, we've got a kid going, this is for NASA, and we'll give it NASA. I can't believe it. But we got images on the 27th of September. So a couple of days after impact. Looks like a puffin coming into land, I think. And then on the beginning of November, you can see the whole tail all the way across. And I think that's something that actually was surprising for the DART mission team. They didn't expect the tail to be so long and to last for so long. So whilst Tim Lister at LCO was taking lots of shorter exposures for measuring the light curve, we were taking longer exposures to supplement the tail set. And we've got some color data from the 2-meter telescope that Tim is going to analyze to see whether you can pick up something more about the composition of the asteroid from that. And then, as you can see, we're getting quite excited because Nancy Chabot, who's one of the DART mission team, was saying, "Oh, that's good." And then we tricked them into doing real science. So we put this up on screen and said, "This is your image, right? If every pixel is 33 kilometers, how long do you think the tail is?" So you all sit there with the calculators and come up with an answer. And then we put a finer grid and a finer grid and a finer grid so that they got a better estimate of what they were doing. If you want to hear the story about the little girl on the right, find me a coffee. She's my trainee nerd. There's a story there. And this is where help from Tony and Richard is really important because they've been doing it literally on a Teams call with, well, the teachers are actually doing the analysis with the kids. They're there, so, oh, do that, nudge that, and etc., which is great. And proper science. Loads of ones on Richard's 29P, the active asteroids. We've parallel with JWST, got a couple of theses, do you call theses? And hopefully there'll be a mine as well when we get to that. And the DART data. The particular school, this is St. Mary's, have extended it. They say, oh, we like this. So they're now doing after school astronomy clubs. They did the Green Comet as well. Lots and lots of engagement. Kids love it, mostly. Quizzes are boring, I was told, but apart from that, and apparently they're already going, is Helen coming in to do rockets next week for the end of term? So I'm doing that next week. And then this was this week in the National Astronomy meeting in Cardiff. And Andy Rifkin, who is one of the DART mission team, was doing the plenary session. And we'd already done a presentation in the morning to the education and outreach session. And so Ben Wooden, who was the teacher, was in the plenary with us as well. And I'd been talking to Andy beforehand. So I said, any chance of a shout out, Andy? Look, St. Mary's Primary. And Ben, who is a big bloke, he's really quite tall. And you met Ben in Prague. And Ben just went, and I thought, that's why I do this. So we're actually getting real engagement, real science with primary school teachers. And we've got lots of resources. Like, you can come and have a look at our rotator. We've got kits if you want to borrow them. If you want to borrow our meteorites, fine. If your school wants to get involved in actually doing the observations, come and talk to us. Really, I think this, am I an enthusiast? Sorry. I will stop at that point, I think.
Helen, that's absolutely fantastic on so many levels as well. I mean, bringing kids into science, it's a really important thing to do. And to do it, as you say, almost kind of tricking them into learning this stuff is great.